So the next thing we're going to need is some reminders about equivalence relations and quotient sets. So let X be a set and E a relation on X. Okay, so things like we've got these statements X, E, Y, which are defined for every pair of elements X and Y, and they might be true or might not be true. Okay, so X, E, Y could mean X is less than or equal to Y, or X could be the integers, and X, E, Y could mean X is equal to Y mod 10 or something like that. Okay, and we remember we say E is reflexive if XEX for all X. Symmetric if XEY is equivalent to YEX. And transitive if XEY and YEZ implies XEZ. For example, if we look at the integers, then we could have the order relation. X, E, Y means X less than or equal to Y, then E is reflexive and transitive, but not symmetric. Because X less than or equal to Y is not the same as Y less than or equal to X. But if XEY means X minus Y divisible by 10, then E is reflexive, symmetric, and transitive. That means it's an equivalence relation. Okay, so that's the definition of what we mean by an equivalence relation. An equivalence relation is a relation that is reflexive, symmetric, and transitive. So if E is an equivalence relation, then we define square bracket X, or we might write it as square bracket XE if we need to specify what E is, to be the set of those T and X such that XET. So yeah, some basic properties of these sets square bracket X, which are called, remember, this is called the equivalence class of X. First key property is that square bracket X is equal to square bracket Y if and only if X and Y are related according to our equivalence relation. Secondly, that X lies in square bracket X. And thirdly, if X and Y are not related, then these sets are disjoint. And it's really this first statement that's the key one. And in fact, it doesn't really matter so much what square bracket X and square bracket Y are. We've defined them to be certain subsets of X, but it doesn't really matter what they are. The key point that matters is just that they have this property here. Square bracket X is equal to square bracket Y if and only if X is related to Y. We define the set X mod E to be the set of all equivalence for classes. Okay, so that's a new set. And And we're going to define pi as a function from x to x mod e. Just by new notation, really. Pi x is going to be the same as square bracket x. So pi is surjective. Every element of x mod e is of the form square bracket x. In other words, it's equal to pi of x for some x. So pi is surjective, and pi x equals pi y if and only if x e y. It's just restating this first fact here in slightly different language. Okay, and so let's. The kind of key thing we want to do with this is define functions from x mod e to some other set. So let's just kind of do an example of that. So let's define EF on Z. My x EY means x equal y mod 4, and x FY means x equals y mod 8. Okay. And I'm going to define a map F from so from Z mod 4, or well, let's say from Z initially to Z mod 8. By f of k is going to be k squared mod 8. Okay, so now suppose, let's say I is related by e to j. So that means that j is I plus 4p, say. So that means that j squared is I squared plus 8p plus 16p squared, which is equal to I squared mod 8. So that means that I squared is f related to j squared, or in other words, that f of I equals f of j. So that means that we can define a sort of induced thing from Z mod 4, a squaring map from Z mod 4 to Z mod 8. So now I want to define f bar from Z mod 4 to Z mod 8 by f bar of I mod 4 is I squared mod 8. I.e. f bar of I mod 4 is f of I. Okay, and this is well defined because, if I1 equals I2 mod 4, then I1 squared is the same as I2 squared mod 8. By this thing that we wrote a minute ago. Okay, and writing this in terms of E and F, it's just this statement that I e j implies f of I equals f of j. Okay. So this is a kind of extremely common line of argument. That you want to define some function from a quotient set to another set, and we use this kind of line of argument. You sort of define your f bar, and you need to check that it's you need to check it's well defined. To check it's well defined, you have to show that some other function f is compatible with the equivalence relation in an appropriate sense. So we just need it's a very common line of argument, and we just need some general ideas, some general terminology to encapsulate it. The general framework is going to be like this. X be a set. With an equivalence relation E. And let f from x to t be a function. And we say f is E saturated if whenever x, e, y we have so whenever 2 points are related by our equivalence relation, then they have the same image under f. So as a kind of key example of that, the projection pi from x to x mod e has pi x equal pi y if and only if x, e, y. So pi is certainly E saturated. So it follows that if f bar from x mod e to t is any function, then the composite, let's call it f, which is f bar composed with pi. That's a map from x to t. That'll be E saturated. On the other hand, so the other way around, suppose f from x to t is E saturated. So I want to define f bar from x mod e to t by f bar of c is f of x for any choice of x. If pi x equals c. Okay. Okay, so this c is supposed to be a point in x mod e, and we know that pi from x to x mod e is surjective, so we can always choose an x with pi x equals c, and then we're looking at f of x. And this is well defined. Yeah, this is not obviously well defined because we had to choose an x, and what happens if we chose a different one? If x prime also has pi x prime is c, then well, that means that pi x equals pi x prime. Therefore, x is related to x prime. That was the key property of this pi, that pi x equals pi x prime if and only if x is related to x prime. And that means that fx is fx prime. That's because f is E saturated. Okay. So f bar is well defined. Okay. So what's the punchline of this? The conclusion is that I'll write in a second, is that E-saturated maps from X to T, they biject. There's a one-to-one correspondence between E-saturated maps from X to T and maps from X mod E to T. Okay, so just to write our conclusion again. So E-saturated maps X to T correspond to arbitrary maps from the quotient set X mod E to T. Works for any equivalence relation E on the set X and any arbitrary set T. And, so that's how. And so in the example we mentioned a moment ago, we had this obviously well-defined squaring function from the integers to Z mod 8. That corresponds to this less obviously well-defined, but in fact well-defined map from Z mod 4 to Z mod 8, f bar of I mod 4 is I squared mod 8. So this whole story about saturated maps is just kind of a codification of the way that we defined this map f bar.